Previously, we looked at resistors in combination, and now I'd like to go and take a look at capacitors. So a lot of the same ideas will apply, but we'll notice that there will be some differences. So first, let's take a look at capacitors in parallel. P-A-R-A-L-L-E-L. So here I'm going to imagine we have a battery. Capacitor 1, capacitor 2, like that. And we can check that these are in parallel by mapping the potential zones. Now when you do this for capacitors, the idea is you just draw right around the plate, like that. So no need to skip in front of it, you can just draw around the plate. There. Everything in red is at the higher voltage, because remember the long dash on the battery is the positive terminal. And we can go and map out the lower voltage side. There we go. So everything here is this plate and this plate are both on the red side. That plate and that plate are both on the blue side. So red, blue, red, blue. That makes these two capacitors in parallel. So if we think about the charge held on the plates, remember this is going to be plus Q1. It's going to be minus Q1. This will be plus Q2. Minus Q2, like that. What we'll have is that the Q1, for instance, will equal C1 times delta V, which in this case is C1 times the battery EMF. Okay. And we can say the same thing for capacitor number 2. C2 times the capacitor battery EMF. Okay. Now, as far as the battery is concerned, it looks at and says, hey, I just moved some amount of charge Q. It doesn't know that there are two capacitors hooked up to it. It just knows that it moved some amount of charge Q off of the negative plate and onto the positive plate. Or more precisely, moved the amount of electrons off the positive plate and over the negative plate. Now, here we can look at this and say, well, when we move charges from the one side to the other, you had to move Q1 for this one, Q2 for that one. So that means that the total charge Q moved has to be Q1 plus Q2. All right, but here we can say for my C equivalent here that this Q would have to be C equivalent times delta V, which will be C equivalent times the battery EMF. So putting in, we'll have C equivalent times the battery EMF equals C1 times the battery EMF plus C2 times the battery EMF. All right. And we can cancel out the EMFs. And if we have more than two capacitors, we can just keep this going. So in general, if I have N capacitors in parallel, C equivalent is going to be C1 plus C2 plus and so forth until you get to the nth capacitor. Now, you should note here that this is the opposite of the rule for resistors. With resistors, remember, it was if they were in series, you'd add them up. With capacitors, it's if they're parallel, you'd add them up. One way maybe to motivate this a bit is to think back and remember that when you look at this line here, This just means low resistance electrical connection. Nothing says that it has to be a wire. In fact, one way you could totally do this would be just to literally weld this plate onto that plate and this plate onto that plate. That would work. But if you weld the two plates together, what you've now done is you've made a capacitor whose area is the sum of the areas of the original capacitors. So the capacitance, since capacitance is proportional to the area, the capacitance would have to go up. So hopefully that's how I tend to remember it. Hopefully that will make it a little easier. Now let's go and take a look at what happens if we're in series. So again, here's the battery EMF. Now we're going to have C1, C2, like that. Okay, now if I go and take a look at this, whatever charge I pulled off of, whatever electrons I pulled off of this plate, I had to stick them over there. So if this is charged plus Q, that plate has to be minus Q. Now let's start to think about what's going to happen in between. So what's going to happen in between here is I got a pile of charge plus Q here, minus Q here. And while we're trying to get to an equilibrium, what's going to happen here is we're going to build an electric field like so. That's going to pull electrons off of this plate and up to that plate. All right, so at least we've worked out that this plate's going to have to be positive, that plate's going to have to be negative. But how much is the charge going to be? Well, it's going to be, no surprise here, Q again. And the way I'm going to argue this is as we're moving charge, yeah, there we go. So we're moving charge. The charges here are moving because if it's an electron being pulled off of here, the electric field line that we have running from the outer plates is running down. Electrons negatively charged, they'll feel force up, migrating it up. Now, as I start to make this negative here and this positive, what's going to happen? I'm going to start running an electric field the other way. So the force moving since this is going to start canceling out the field from the inner plates. It's going to start canceling out the field from the outer plates. And so it will be less capable of moving charge. And this will all come to an end when this is plus Q and minus Q, because really the difference in distance here is so negligible. All right, so what we've worked out is that this has to have a charge Q. That has to have a charge Q. So we can say here that Q1 equals C1 delta V1, or sorry, just Q. And likewise, here, Q would have to be C2 delta V2. Now, probably a little cluttered to draw the potential zones, but it's worth it, so I'm going to redraw the circuit so that we don't have both potential zones and field lines sitting in the same drawing. All right, so let's go ahead and map the potential zones. So again, we'll start with the positive side of the battery, go here, and remember with capacitors, you just go around the plate when you're mapping the zone. There, that's my high voltage zone. Let me go ahead and draw my low voltage zone. And then finally, I have to have something in between. There we go. So what I'm getting here is that the voltage across the first capacitor, that's going to be my delta V1. This is going to be my delta V2. But we can recognize that the battery EMF would have to be equal to delta V1 plus delta V2 for the voltage zones to make any sense. All right, now if I'm going to replace this with an equivalent capacitor, and again, equivalent as far as the battery is concerned is one where you move the same amount of charge. So this will end up having a charge plus Q minus Q, and so here we would be saying that Q is equal to C equivalent times the battery EMF. All right, so let's go ahead and take this thought here. In fact, let me just rewrite it here. The EMF is equal to delta V1 plus delta V2. All right. So if I go and take a look at this, I can rewrite this for the EMF by dividing by C equivalent. I'll get that it's equal to Q over C equivalent. So this will be will be Q over C equivalent. This will be, by the same logic, Q over C1, Q over C2. All right. So we can go ahead and cancel out the Q's like that. And if we rearrange this, we'll get that C equivalent is equal to 1 over C1 plus 1 over C2. And if I have n capacitors, this is just going to keep working up to the nth capacitor, however many that is. So the rules are the opposite of resistors. My advice is you'll probably find either the rules for capacitors or the rules for resistors more intuitive. Just learn those and then remember that the other ones are opposite. Okay, so let's just do a couple quick examples of this just to get some sense of how this might work. Let's first take a look at a parallel combination. So let's say I've got a 2 microfarad and a 3 microfarad capacitor in parallel. All right, since they're in parallel, and if you're not sure if they're in parallel or not, go ahead and map the potential zones. There you go, red, blue, they're in parallel. So since they're in parallel, we know that what we do is we add them up. So we'll call this one C1, call this one C2. So this will be 2 microfarads plus 3 microfarads gives us 5 microfarads. All right, now let's take a look at a straightforward series combination. So let's say I simply have 2 4 microfarad capacitors in series. And again, you can check that something is series by just saying, if I run my finger along this, if it does not so the gray line here is me running my finger. If it does not run through any junctions, then it's in series. So sure enough, no junctions, it's in series. All right, So since it's in series, C equivalent is going to be 1 over 4 microfarads plus 1 over 4 microfarads. All right, so that'll be 1 over 2 over 4 microfarads, which is 4 microfarads over 2 is 2 microfarads. So the rule of thumb here, if you are in parallel, the equivalent capacitance should be bigger than the biggest element you got. If you're in series, the equivalent capacitance should be smaller than the smallest element you've got. So in this case, 2 versus 4, 5 versus 3. Both of those check out. If you get something more complicated, you can play the same game that we did earlier with resistors. So let's try this one on for size. So I've got 2 microfarads here, 2 microfarads there, 1 microfarad there, 2 microfarads there, and what I'd like to know is what is the equivalent capacitance of the entire network. So again, this is a divide and conquer kind of thing. Your whole idea is to find the smallest piece that you can where you actually have something that's series, that's either series or parallel. In this case here, I recognize that these two capacitors are in series, because if I run my finger from one to the other, it does not pass through any junctions. So I will first look at that right there. So since that's in series, the equivalent capacitance of that is going to be 1 over 2 microfarads plus 1 over 2 microfarads. So that will be 1 over 2 over 2 microfarads. So it'll be 2 microfarads over 2 is 1 microfarad. Now what we do is we redraw the circuit, replacing this with its equivalent. So, whoops. There we go. And let's draw this one in purple, just to remind us it's an equivalent that we've already found. So this is the 1 microfarad equivalent capacitor there. And then we have 1 microfarad, 2 microfarads, 2 microfarads. All right. Now, if I look here, I've got these two in parallel. And honestly, I could have started with this pair to begin with, but I didn't. I got these two in parallel. I got these two in parallel. So let's go and take care of them more or less at the same time. So we'll do that parallel combination, and we'll do, whoops, there we go, that parallel combination. So capacitors in parallel add. So this will be 1 microfarad plus 1 microfarad is 2 microfarads. And this one will be 2 microfarads plus 2 microfarads is 4 microfarads. All right. So we can redraw the circuit again. So now I've got a 4 microfarad equivalent capacitance there. And I have a 2 microfarad equivalent capacitance there. And I can run my finger along that and see that they're in series. And so finally, I can find the equivalent capacitance of this. This will be C equivalent. So if you're in series, you add in reciprocity. It'll be 1 over 2 microfarads plus 1 over 4 microfarads. So that's 1 over 2 over 4 microfarads. Just trying to get a common denominator happening here. So it'll be 1 over 3/4. So this will be 4/3. Oops. Microfarads. All right, there you go. Now, the same caveats as before exist. It is possible to have combinations of capacitors that are neither series nor parallel. If that's the case, you have to resort to using Kirchhoff's laws. We'll just focus on how to do that with resistors, but the same in a later video. But the same ideas would apply if you had capacitors. All right, so in the next video, we'll take a look at what happens if we have a series combination of a resistor and a capacitor. Catch you over there.